So it's amazing to have Kate Selway here with us today. Kate is a senior research scientist with the MinEx CRC at the University of South Australia, and she'll be speaking to us today about magnetotellurics. That's such a tongue twister, that one, for mineral exploration. She will go through what MT is and when it will and won't be useful in exploring, from looking at depth to basement, crustal features, and the whole of the lithosphere. So thank you so much, Kate, for coming. It's just wonderful having you.
Excellent. Well, thank you. Gosh, thanks so much to Jess for inviting me to be part of this. And frankly, thanks so much to Jess for setting up and organising the whole GeoHug thing. I think it's a fantastic initiative, and it's great that it's been so successful. And I've certainly never given a talk where I've had an intro act before. Yeah, I love it. It's fantastic. So I'll be talking about magnetotellurics for mineral exploration. Jess is right, it's a hard word to say. We normally just say MT instead to save ourselves the trouble. And talking about how MT can help exploration from the near surface through to the deep earth. This talk is really going to be aimed at explorers or people who are interested in mineral exploration. And I guess it's, you know, certainly within Australia, we are doing a lot of MT these days, and a lot of that MT is aimed at the ultimate goal of trying to find more mineral deposits. It was sort of almost 20 years ago when I started my PhD in MT, and at that time, it was not a technique that people knew about. You know, when I was giving talks, I was really introducing the idea of MT to the geoscience community, and it was not something that most people were familiar with. Fast forward to now, you know, we have these incredible programs like AusLAMP, where the government's funding a lot of MT aimed at mineral exploration, and also individual companies doing a lot of MT themselves. And so that's a fantastic transition. But I also feel that, you know, from talking to people, I get the impression that there's still some uncertainty on exactly how that MT data, how those models can actually be useful in a practical sense for exploration. And so that's what I'm hoping to talk about today. And in a few different ways, I guess, partly that there are some things that MT won't be useful for. And so if you're coming to your exploration with those kinds of questions, then it's useful to know what MT is not going to be able to help you with. But also that there are certainly ways that the MT data that we're currently collecting could be better utilised. So I'm hoping to kind of give an overview, as I say, from the near surface to the deep earth to talk about those things. And it's just that I've been lots of different places recently, but I'm now very happy to be at UniSA with the MinEx CRC. So as I say, I'll be talking about three different scales that we might want to use MT for mineral exploration. Firstly, the most shallow level, using MT to get depth to basement. Then moving into the crust, looking at the deposit and camp and really the whole sort of crustal scale of exploration. And then moving into the mantle and looking at how MT can be useful for lithospheric scale exploration. And as I do that, I'm going to be considering two questions. And that's, in what circumstances will MT be a useful tool for you in exploration? What are the questions that MT can actually help you answer? And sort of tied up with that is then which scenarios or circumstances or compositions will produce conductivity contrasts that we can see with MT. I'm going to start with, I think, just two slides on what MT is. As I say, sort of back in the day, half the talk needed to be this. I think most people have some familiarity with MT now. So I'm not going to talk about this too much, but just to get some principles that are really useful to keep in mind as we think about what kind of questions MT is going to be useful for answering. So MT is an electromagnetic geophysical method. And like all EM methods, whether it be frequency domain, time domain EM, airborne EM, there's a time-varying magnetic field. It induces currents in conductive bodies within the Earth, and then we can sense the secondary fields that come from those currents. The difference with MT is that that primary magnetic field is the Earth's magnetic field. So this means that the signals that we're using in MT penetrate much more deeply into the Earth than active EM methods. So the big difference then with active EM methods is that MT can image deeper into the Earth, but it also means that it doesn't have as good shallow resolution as some of those active EM methods would have. So because of this, what we're seeing with MT is conductivity. So at a first level, MT is only going to be useful for you if what you want to see has a conductivity contrast. If what you're wanting to image has a density contrast but no conductivity contrast, MT is not going to help you. You obviously need to do a gravity survey instead. A bit more deeply, so MT is sensitive to conductivity and to conductors rather than resistors. So on the figures here are some theoretical resistivity depth profiles through a theoretical lithosphere, where the blue line is that input resistivity depth structure. The horizontal axis is resistivity, so resistivity is increasing along the x-axis. So our conductors are these features down here, for instance. The red line is then, if we forward model that data and invert it, then the MT response that we would get. So you can see here that the MT has picked up this conductor really, really well. It's resolved the depth to that conductor. It's resolved the resistivity of that conductor. But this resistive layer that sits directly beneath that conductor is not resolved well at all. We're not seeing this sharp boundary at the base of the conductor, and we're not at all picking up the absolute resistivity within that resistive region. And that's just the physics of how MT works. There's not really, we can maybe tell that we're not resolving this layer well, but we're not going to be able to image the absolute resistivity of that resistor very accurately. So important thing to keep in mind, good at imaging conductors, not good at imaging resistors. And what it images best is the conductance, which is the conductivity times the thickness of that conductor. Another important point is that it's sensitive to the geometry of those conductors. So if you have a conductive phase, but it's disseminated within your rock and those minerals are not interconnected, then MT won't see that as being a conductor. The conductive phase has to be interconnected for MT to be able to image it. So with that, that's all the backgrounds. We're going to move now into how MT can actually be useful at these three different depth scales. So firstly, looking at depth to basement, obviously a really important question in exploration, and becoming more and more important as exploration moves deeper under cover. And some of the cover that in the past, maybe we could just use active EM methods to image beneath the cover sequences that we were interested in. But now exploring beneath deeper cover, those active EM systems can't penetrate that deeply, so MT is being used to try to image that depth to basement. So MT, as I say, then MT will be a useful tool then when the depth to basement is greater than can be imaged with active EM methods. Obviously, we need a conductivity contrast. If there's no conductivity contrast between the cover and the basement, MT is not going to show us the top of that basement. The real challenge from that point that I was just making in the last slide, the real challenge in imaging depth to basement with MT is that generally, at least within Australia, the cover is much more conductive than the basement. And as we just saw in that kind of situation, that imaging the depth to the top of that resistor and also imaging the resistivity of that resistor is not something that MT is by nature very good at. So why do we have a conductivity contrast? We can, at least within Australia, we can generally expect that we will have a conductivity contrast, normally really because we've got so much salinity within our cover sequences, also clay layers, but really that salinity and any moisture within those sedimentary layers mean that those sediments tend to be really highly conductive. And then the basement tends to be more resistive, although it's also important to note that if there's a weathered layer at the top of the basement where, maybe there's some cracks and fractures and some of that salinity is getting down into the top of the basement, that conductivity contrast will then really be with the top of the fresh basement rather than the top of the weathered basement. I'm just going to show you a really nice example using MT for depth to basement that's just recently been published. This is work that has come out of CSIRO and the Geological Survey of Queensland. And this is a really big MT survey in the Cloncurry region of Queensland. I can't recall exactly how many MT sites this was, but it was several hundred. And the goal of this work was to use MT to image depth to basement. I've given you, I'd really, if you're interested in this question, I'd really recommend having a read of this paper. So I've given you a link to the DOI there and the title of the paper. And if you don't have access to get your hands on it, I'd recommend emailing the authors because I've no doubt they'll be happy to send a copy. So in this work, they were, as I say, looking to use the MT for depth to basement. A bit about the region that they were in. There's a magnetic map of the region where you can see a couple of features. Most importantly, these large faults which have a big magnetic response. And also there's a lot of drill holes already in the region, which is kind of a good test then against the MT to see how well the MT is doing at constraining the depth to basement. So these drill holes show that the depth to basement increases to the north, and it also increases as you cross over the Mount Margaret fault. This is some visualizations then of the MT data that was collected. These aren't inversions, these aren't model responses. These are just sort of plotting up the data themselves in a couple of different ways. So at the top, we have some panels of, this is decreasing frequency going across. So again, it's not an inversion, so we're not in depth space here. We're looking at the data, which are in frequency, but this decreasing frequency sort of corresponds to increasing depths as we go from left to right across these panels. And the top panels are really looking at the magnitude of the apparent resistivity. So you can think of it sort of approximately as the resistivity of the Earth that you're looking at, where the reds are more conductive and the blues are more resistive. So as we go across these panels, we see things start out sort of pretty homogeneous and pretty conductive. As we move to greater depths, things get more resistive and showing a similar pattern to what we saw with the drill holes, where the shallowest resistors are in the southwest, and then that resistor moving up with increasing depth. The bottom panels are looking at the phase tensors, which is another way of looking at this data. And the phase tensors are really looking at the dimensionality of the Earth. So if our site is sitting on a sedimentary sequence that's just horizontally layered, and the Earth looks exactly the same in every direction that we look at it in, then those phase tensors are a circle with a sort of greenish kind of colour. As we move down with depth, then we see these phase tensors change from being circles to ellipses, and that tells us that instead of the Earth being the same in every direction, then we start seeing the currents flow preferentially in one direction, which might be an indication that we're getting into the basement. And we see these, the colours of these start to change away from that central green colour as well. So again, a similar pattern to what we saw in the top panels, where these things start to change with depth, suggesting we're getting further into the basement. But another really neat thing that they did in this paper was some probabilistic modelling. And this really highlights what I was saying before, that MT is really good at constraining conductors and the conductivity of conductors, not so good at constraining resistors. So this is resistivity depth sections just through 3 stations, which are shown in the red over here. The exact location of them isn't so important for us right now, just showing that, again, we've got resistivity across the horizontal axis. So conductive things are further towards the left, resistive things further towards the right. In each of these stations where we have conductors, all of these probabilistic models all show exactly the same thing. They all really model those conductors really, really well. Once we get into the resistive layers, these colours show us that all the probabilistic models are really uncertain, and that actually models could fit anywhere along this whole colour band and still fit the data perfectly well. So this illustrates that we're not resolving the resistivity of those resistors very well. And also then as the depth to the bottom of that conductor increases, there's also some uncertainty in the depth to the bottom of that conductor. So these kind of probabilistic models are really useful for highlighting where we have confidence in the models and where there is uncertainty in the models. So also in this work, they then put together those probabilistic models across the whole survey region. And that's what we're looking at here. In these 3 sets of panels, at the top, we have just the median values from all of those probabilistic models of all of the different stations. Again, so our yellows here are more conductive, purples are more resistive. So at the shallowest depths, we're in the sediments and everything's relatively conductive. And as we move down with depth, we start to get into the basement, firstly in the southwest, and then moving up towards the north, with this big jump across the Mount Margaret Fault. The bottom 2 panels show the 5th and 95th percentiles of those probabilistic models. So they're really an indication of the uncertainty in those probabilistic models. So where these 2 models look basically the same, then we have a pretty good understanding that that's exactly what's going on in the Earth. But where they differ a lot, then it shows that there's a lot of uncertainty there. So for instance, at this deepest depth slice, which is about 1,100 metres, across on the eastern side of the Mount Margaret Fault, these models are really, really different. One model has us in a strong conductor, the other model has us in a strong resistor, really indicating that, that we don't have a good constraint on what's happening, what the depth to basement is over that side of the Mount Margaret Fault. So I think a really nice illustration of then in contrast, areas like the southwest of the model, where there's pretty good agreement between these percentiles, that we can be pretty confident from NT of what the depth to basement is, and then the areas where we don't have such good confidence. Moving from depth to basement to further in the crust, and I'm sure for all the Australians watching that most people are familiar with this Olympic Dam Fingers of God model, which was probably the thing in Australia that really got people excited about using MT in the first place. Similarly, there are other types of models from elsewhere in the world. This is an example from a porphyry copper deposit in Canada. Again, looking at shallower depths here, we're only down to a bit over 1 kilometre depth here. But again, a really, really strong crustal conductor beneath this ore deposit. So what are the principles that we can think about as we try to understand what might be causing these conductors and how we can use MT more generally as an exploration tool as we're looking in the crust? For, again, those same principles from before, that MT images conductivity contrasts and it's most sensitive to conductors. Then once we get into sort of the crystalline crust, the vast majority of crustal minerals are strongly resistive at crustal conditions. So this is just a compilation plot of the conductivity of a bunch of sort of pretty typical crustal minerals. At crustal temperatures, if we're in tectonically stable crust, so we're somewhere in this kind of temperature range, a few hundred degrees, those minerals are all quite strongly resistive. We'd be looking at resistivities of maybe 10 to the 4, 10 to the 5 ohm meters for pretty standard crust. And that's illustrated here. These are some sort of crustal compositions put together for pretty standard crustal compositions, whether that crust be totally dehydrated or contain some hydrous minerals. Either way, if we forward model what our expected resistivities for those crusts would be, we're looking at resistivities of 100 to 1,000 to tens of thousands of ohm meters. So pretty resistive, and even that 100 ohm meters is only sort of right at the base of the crust if that crust is quite hydrous. We're looking, normally we'd be expecting thousands to tens to hundreds of thousands even of ohm meters. This is actually a really useful tool as we try to think about MT for exploration in the crust, because there's actually very few options in tectonically stable crust. If we're not going to have any melt and we're not going to have any saline fluids, there's very few options that could be causing really strong conductors in the crust. And really the key options are graphite and sulfides. So this is then a compilation of some of the minerals that might be a bit more conductive in the crust. And again, in this kind of stable, tectonically stable temperature range, this top blue line here is graphite. If we're looking for something that can cause an anomaly of 10 or 100 ohm meters, it's really only graphite. And then here's the conductivity of sulfides, which would also give us those kind of strong conductivities. And really that's because the temperatures are low enough in the crust that it's only materials that will undergo metallic or ionic conduction that will be significantly conductive in the crust. So if we compare that to these kind of MT models that we see associated with mineral deposits, but also we see a lot of crustal conductors that are not associated with mineral deposits. The conductivities of these strongly conductive zones, both associated with the porphyry system in Canada and also with Olympic Dam, we're looking at conductivities of 10 ohm meters, give or take, some even lower than that. So that's at this kind of level here, and where are we? This kind of level here. So sulfides can certainly do it. Graphite can do it. Not too many other minerals can do it. So that's actually, as I say, that's a really useful tool that we actually don't have too many options of minerals that can explain these conductivities. I think one really important step that's still needed in making MT really useful in exploring within the crust is developing models of our ore deposits and the whole mineralizing systems that incorporate those expected resistivity responses. So for instance, this is part of that Canadian porphyry copper study where this sort of hypothetical porphyry system was modelled with its expected magnetic response, its expected chargeability response, and also its expected MT response. But even things like this are pretty few and far between, and this is obviously a pretty simplistic view of a porphyry system compared to maybe a more up-to-date view of a porphyry system. while building those models, it's really important to recognise also that any conductive minerals within those deposits or those ore systems need to be connected. So, for instance, if you're expecting there to be sulfides within your system, but those sulfides you're expecting to be disseminated, then they won't produce a conductor that will be imaged with MT. And this is just actually another study that was part of this porphyry study, showing that disseminated sulfides don't really produce a conductive response, and their conductivity will be a couple of orders of magnitude. The conductivity will be lower, resistivity will be higher than if those sulfides are interconnected in continuous veins. So I think this is really an important step that both explorers and us in academia need to be working on, to build these kind of models to understand what we would expect the MT response to be of different different deposit systems, so that MT can be a more useful tool for exploration. Moving deeper into the mantle, and one question might be, why would we bother looking into the mantle? Obviously, it's going to be, even if there are deposits down there, it's obviously going to be much too deep to mine them. And really, it's because for many mineralizing systems, and particularly for giant mineralizing systems, for those systems to form, the mantle is a really vital part of that system, and a sort of a necessary component of many of those giant ore systems is to have a fertile mantle that is really then the source of the minerals that end up being in the ores. So obviously we're not looking at the mantle for the mantle itself, but we're looking to the mantle to then get an image of places where there might be these giant systems that then might be worth looking at in a bit more detail in the crust. And this is described in, for instance, this is a paper of John Bronski's looking at giant gold deposits that then within this mineral systems model require a fertile zone within the upper mantle, require some lithospheric scale structures that fluids can move along and bring that fertility from the mantle into the crust, and then a subsequent remobilisation event to concentrate that into ores. Similarly, in these sort of cartoons from Bill Griffin, showing really basically within the mantle, we're looking for these dark green zones, and these are zones that will be geochemically enriched, they'll be fertile, and they will have experienced mantle metasomatism, fluid rock interaction, that's basically going to have mean that the mantle's full of all of these goodies, that then subsequently there's melt or fluid that passes through that then brings all of those goodies up to the crust and forms our deposits. And certainly through looking at a lot of things, including the geochemistry of these systems and even just their association with mantle rocks. The greenstones is a great example of this, that we know that many of these giant systems have this mantle involvement. So MT can be really important in that picture because when we're looking at the mantle, MT really directly responds to mantle metasomatism. So MT essentially is really good at seeing these dark green zones within the mantle. So why is that? Some principles behind that. So again, most mantle rocks are pretty resistive. Once the silicates that make up the mantle, olivines, pyroxenes, garnets, are semiconductors. They're relatively resistive. Their resistivity decreases with temperature. So it's just the same as those crustal minerals, really, that as we make them hotter, they become more conductive. And the other really important thing that affects their resistivity is defects within the mineral lattice of hydrogen or hydroxyl or water. so some resistivity depth plots through, again, some hypothetical mantles here on the right. The proportions of olivine and pyroxene don't matter too much. That's what these different plots are in the top plot. But once some of these hydrogen or water defects get into those minerals, then it does have a substantial impact on the conductivity. It makes those minerals a lot more conductive. And so importantly, that hydrogen that would get into those minerals, it's water that's going to get into those minerals because there has been some fluid rock interaction. And all of the factors that increase mantle conductivity are related to past fluid rock interaction within that mantle. So that high conductivity can be caused by, like I just said, hydrogen within those minerals, olivine and pyroxene, that are nominally anhydrous. It could be caused by actually hydrous minerals themselves, minerals like amphibole or phlogopite, which have a relatively high conductivity, or also graphite to the extent that it's stable within the mantle as well. For any of those things to be in the mantle, they have to have been brought in by a metasomatic event, by some fluid or melt interacting with that mantle. And yeah, it's really important, a really important point. Not all metasomatism is going to create these conductive zones in the mantle, but really whenever we see a conductive zone within tectonically stable lithospheric mantle, it signifies that there has been past metasomatism, and essentially that mantle is one of these fertile dark green zones. So obviously, as we look deeper into the Earth, our interpretations become more difficult because we just have less rocks and we know less about the composition of the Earth to compare our interpretations with. So one thing that we've been doing with trying to improve our interpretations of mantle MT has been looking at the Kaapvaal craton, where we have really fantastic MT data collected with the SAMTEX project. And there's also, obviously, loads of kimberlites through Southern Africa that have brought up lots of diamonds, but also brought up lots of xenoliths, so that we know the composition of the Southern African mantle really better than anywhere else in the world. So the xenoliths give us information like this, just the mineralogical composition of the mantle with depth, the magnesium number of the mantle, the geotherm, and we also have actual hydrogen content measurements on minerals that have been taken out of those xenoliths as well. So it's a really good place for us to, because our goal was to firstly check that our interpretations of our MT data were sort of on track. These interpretations come from experiments that are done, somebody taking a tiny olivine grain and putting it under a really high pressure and high temperature and measuring its conductivity, checking that those calculations, when we extrapolate them to the entire mantle, are still we're still on the right track. And also seeing if we can understand a little bit more about the mantle composition than through using MT. So this is work that was headed up by Sinan Ozaydin, who's my PhD student, who's just very recently finished his PhD. So he brought together all this compositional data from the xenoliths, got the MT data, modelled up the MT data, just showing again, we're running again these probabilistic 1D models of MT looking into the mantle, and exactly the same principles apply, where we can resolve the conductivity of conductors really well, but can't resolve the resistivity of resistors very well. And in a general sense, when we're looking at the mantle, because the crust tends to be a bit more conductive than the mantle, the uppermost mantle, then we tend to not be able to resolve very well. It should theoretically be extremely resistive, And as you can see here, in this kind of depth range, at the top of the lithospheric mantle for the top few kilometres, because it's then a resistor sitting underneath a conductor, we don't have a good resolution of those resistivities. And that's something we see quite often in a lot of places. And so then by comparing the MT results and the MT interpretations with those compositions from the xenoliths, we could see a few things. We could see firstly that our interpretations from the MT were basically on track if we just had the MT data and interpreted the composition and the geotherm and the hydrogen content from that MT data. We would be agreeing pretty well with what we see in the xenoliths, which is great. And that's sort of what we're seeing here. This is in the shaded colours. This is the interpretations from the MT using a few different experimental models, experiments that match composition with conductivity. And then the black circles is the water contents measured from xenoliths. So you can see we're agreeing pretty well, but we can also see that some of these experimental models, here particularly the green one, which is an early model that's been superseded, don't match the xenolith data very well. So then we can get more certainty that those are models that we should be setting aside and not relying on so much. We can also build then sort of from that recognition that our interpretations are basically on track. We can also start to build a slightly deeper understanding of what we're seeing about the metasomatic history of that piece of lithosphere. So for instance, at the shallower mantle levels, sort of 100 to 125 kilometres depth here, geochemically more fertile layer, there's more pyroxenes, there's more hydrous minerals, there's quite a lot of phlogopite within this layer. And underlying that is a more geochemically depleted layer, there's less pyroxenes. And in the MT conductivities, the conductivity decreases in a depleted layer and is more conductive in the fertile layer, which is maybe what we would expect. But we can see, in contrast, that the water contents measured from the xenoliths are pretty constant through those layers. From that, we can start to get an understanding of how the region has been metasomatized and how the kimberlites and the xenoliths may not actually be very representative of the whole region. For instance, if you consider that a kimberlite is really just a point measurement, and a xenolith is very, very much a point measurement of the composition of the mantle, whereas geophysically we're imaging really a bulk average of a large amount of mantle. So here within this fertile layer, we've interpreted that what we're seeing is that the previous metasomatism within that fertile layer really expanded out laterally, and that's why we are imaging it with the MT. In the depleted layer, that metasomatism seems like it just affected really the area of the kimberlite pipe and didn't expand laterally out. And so that's why we don't see an extensive conductor in that depleted layer. So just an example then of how the MT can be used to really interrogate a bit more deeply the metasomatic history of a piece of mantle, and build up a model that can then, if we're then looking at a region for exploration, to know which regions have been metasomatized. And again, if we build that into our exploration model, to know if we know what types of metasomatism, maybe what depth of metasomatism are going to be important for prospectivity, then we can use that to know which regions to focus on. Yeah, the next step is really then to, now that kind of, I guess we have this calibration, we can be confident that our mantle interpretations are basically on track. For developing this as an exploration tool, especially looking at the mantle, I think the next really important step is to understand known systems to do MT surveys over some known giant deposits that will have a mantle signature, understand what we're seeing there, and then be able to take it to some greenfields regions. And this is certainly, I'm doing some working with the West Australia Geological Survey and the University of Western Australia, doing this work over Kaapvaal in the Eastern Goldfields region. So just to summarise that, so I've talked about what MT can do well, and what it does well is image conductors and image to depth. It can image to hundreds of metres depth if we're looking at depth to basement, or hundreds of kilometres depth if we're looking at lithospheric scale exploration. It can't resolve the resistivity of resistors well, and it's not good at imaging features directly, especially resistive features, directly underlying conductors. So if that's your target, MT might be able to help you a bit, but there might be better tools to try to image those things. When we're looking at depth to basement, the pros of MT is that it can image through deep conductive cover that might be too deep for active source EM systems to look through. But really the challenge with MT for depth to basement is that the top of the resistive basement below that conductive cover will be poorly resolved. Sorry for that typo there in cover. Yeah, it's not going to be able to resolve the exact depth of that resistor or the resistivity of that resistor underlying a conductor very well. But as we could see in the probabilistic modelling from that Cloncurry example, it also depends, on the exact thickness of your cover and exact conductivity, and through those probabilistic tests, it's a good way to be able to check how well those features are being resolved. In the crust, I think really one of the pros of using MT is that there's only a small number of candidate minerals that can explain anomalous conductors that we can see. So if we're trying to then understand the composition of our crust and the geological process that have happened to it, we have a reasonable chance of knowing exactly what the mineralogy is that we're looking at. I think the challenge for the whole community is to then build conductivity responses into ore deposit models and exploration models so that MT can be a more kind of useful practical tool. Within the mantle, really the pro of MT is that all the conductors that we see within tectonically stable mantle indicate that that mantle has been metasomatized, and metasomatism of the mantle is a prerequisite for many giant ore deposits. Again, the challenge is exactly the same as the crust, to build those expected conductivity responses into our ore deposit models. So that if we know, okay, if I'm exploring for a porphyry copper system, what minerals will I expect through the mantle into the crust, and what will the MT response of those minerals be, so that I know if I'm looking at some MT data, I know what I'm looking for, and I know what responses indicate prospectivity, and what responses don't indicate prospectivity. And yeah, I think as an entire community, both in exploration and in academia, I think the really important next step is to build up sort of a library of understanding the responses of known deposits, so that then we can then take those to new greenfields areas in using MT as an exploration tool. Thank you.
Thank you so much, Kate. That was awesome.